6:30. So welcome everyone to the March meeting of the Stockton Astronomical Society. I think we've got a nice program put together. It's good to see everybody in person here and on Zoom. We've got a great presentation. Looking forward to it. We have two tonight. First thing I want to do is I want to pass around a couple sign-up sheets. I'll start over here at the far side of the room. Excuse me. Bill, circulate these through. We'll pass them around. We're passing around two sign-up sheets. One's for refreshments. That's the important part of the meeting, right? And in fact, you guys in Zoom, you're missing out because everybody's already dug into the chocolate chip cookies here. So the other sign-up sheet is the March and April public outreach events that we want folks to sign up for. Doug's got the announcements on that later in the meeting. We'll go over that. But we're looking to, if you're interested in joining the public outreach events, please sign up on those sheets. Okay, I wanted to welcome any guests that we have, and I see everybody in the room here is a familiar face. We've met before, and those folks on Zoom, I think we know everybody on Zoom as well, don't we? Yeah. If there's
Hi. Last name? Payne. Mike Payne? All right, good luck.
Mike, yep, thanks for coming out. We have the normal agenda for tonight. We've got a presentation and then another presentation, then some announcements. So stick around to the end of the meeting, and then we'll be able to also wrap it up with refreshments at the end. So without delaying any further, I'm going to go ahead and introduce our speaker for tonight. One thing I want to say before I do that introduction is we're doing something a little different, where at the end of the presentation, do it for the Q&A. If you're here in the room and you have a question, you want to speak to the presenter and ask him your question, please step up to that microphone back here at the back of the room, right behind Dennis. That way, the camera will be turned on you. The speaker can see you asking the question. You can see him. And I think it just makes it a little bit more connected that way. We're going to try it that way. Okay. Awanish Mishra is our presenter tonight. Awanish is a member of the Sacramento Astronomical Club. And I want to welcome you, Awanish, and thank you for presenting. Awanish has more than 40 years of science and business experience. He holds a bachelor's degree in chemistry with a minor in quantum physics, along with a master's degree in physical chemistry with a focus on quantum mechanical modeling. He is now retired. Congratulations.
Yes.
And as an amateur astronomer, he has been studying astrophysics for over 30 years. So with that, let's welcome Awanish.
Thank you.
And I'll turn it over to you.
Okay, then I will share my screen and get started. First of all, I really want to thank you for this opportunity. It's very nice of you guys to invite me. Let's see, before I get too excited, I want to make sure everything is working. Hopefully you're seeing a proper screen now. Are you? Just give me a thumbs up if you can at the very least.
Yep.
Good, good. So I'm excited to be here. And without wasting any of your time, let's just get into it. And I want to talk tonight about measuring astronomical distances. The one caveat, couple of things I want to mention first is I go through these each time I do the presentation. I update it in some way, and I'm always deathly afraid of some poor grammar or a spelling error. If you detect one, well, gosh, I'll just feel bad for a week or two. But outside of that, hopefully it's all good. The other thing is hopefully you don't have a power failure here in Davis. In all the years I lived in Santa Clara, because I lived near a fire station, I never had a power failure. But here we've had 4 in a year and internet outages too, but hopefully we're all good for right now. That being said, I'll get into it. I was introduced already about my background, but I do want to mention that I hail from the great state of Minnesota. And, you know, the thing that matters on this slide the most to me is that I love beagles, period. There's just no two ways about it. They are the greatest dogs on this planet. I also love cold weather. I hate California summers. I hate California springs and fall, and I've lived here for over 35 years. That being said, I've had the fortune with my buddy John to go to the Antarctica and do a polar plunge in about 2,000 feet of water there. And then a couple of years later, while we were still in good relations with the Russians, we took a nuclear-powered icebreaker from Russia and went to the North Pole and did another polar plunge there. And that was a lot of fun. Had a great time. Bottom line is I love cold weather, beagles, and I love science. In particular, quantum mechanics and general relativity and special relativity. But both of those feed directly into astrophysics, which is a huge passion of mine. Anyways, we'll get going here. Our agenda tonight is vastness of the universe, measuring astronomical distances, and our place in the universe. So it's going to be kind of bracketed on both sides, and in the middle will be several methodologies used by astronomers to measure distance. And now I've discovered one thing, especially in quantum mechanics, is that you know, the English language is great at describing and explaining things, but sometimes language isn't enough. And that's where math comes in. It can describe things a lot better. But I think at the end of the day, if you can't transfer that into some way of imparting information, knowledge to people, then of what use is it? So I'm working hard to make sure we get through this. But if you have any questions, we can talk at the end. But if something is sounding really goofy, feel free to chime in and we'll go from there. So these are the topics. First of all, let's all agree that the universe is large. It is unimaginably large. And because of that, and for thousands of years, since ancient times, we've been fascinated by things that we look up in the sky without knowing how big it really was. You know, it doesn't matter. We're all related to people who looked up in the sky, whether they were farmers or soldiers or sailors or just travelers, whether it was 100 years ago, 500 years ago, or 5,000 years ago. All of our ancestors are doing very similar things, looking up to figure out where they are and where they're going. So in a way, I like to say we're all descendants of astronomers. So that's just the way it is. And I'm a firm believer in that. And along those lines, one of the earliest and most fundamental questions we had was, well, how far away are those lights that we see in the sky? How far away is that bright sun? You know, and how do we figure that out? So that's what we're going to talk about in this talk. Now, the thing that really impresses me the most is everything we do when it comes to astronomy, astrophysics, the most fundamental of the natural sciences, we do it from our chair here on planet Earth. Oh, sure, we've sent a few probes out that have gone barely any distance given the size of the universe. So I consider astronomers to be unbelievably imaginative in how they're able to determine things, figure out the characteristics, and expand our understanding of the universe. So let's get into it. I said space is vast, right? Well, Earth has a diameter of about 7,900 miles, give or take. It averages about 93.5 million miles from the sun. The Kuiper Belt is about 4,675 million miles away from us. And then we have the Oort cloud, which is about 18.7 trillion miles from us, okay? But, you know, we're measuring things in thousands, millions, billions, trillions, and that's barely even getting our tip of our big toe out the front door. These are nothing. These distances are nothing compared to the vastness of the universe. And that's always fascinated me. By the way, I have a tendency to stick with miles, imperial units, but I'll sometimes throw in metric units simply because that's how the world works. In science and math and engineering, you use metric units, and we also use imperial units. So I'll sometimes tend to go back and forth, but if I say one, I'll explain what the other one is as well. So again, astronomical distances are ginormous, and I mean that from a technical term. On a day-to-day basis, the stuff that we're familiar with, inches, feet, yards, cubits, whatever, miles, they're insignificant. So our set of rulers for our regular daily life doesn't really apply when it comes to astronomical distances. So astronomers have developed a new set of rulers that work for them. And I want to just go over them real quick because that's the basis of a foundation of what we'll talk about. First of all, there's the astronomical unit, which is the average distance. One astronomical unit is the average distance between the Earth and the Sun, about 93.5 million miles. As you all know, it varies where we have an elliptical orbit around the Sun, so it's not exactly that, but that's on average. So Pluto is 3,669,000,000 miles away, or 39.47 astronomical units. You take those miles, divide it by 93.5 million, you get roughly 39.5 astronomical units. Going up the ladder, we also have what's called a light year. And that's the time it takes light to travel in 1 year. Surprising how at different gatherings I've been to, there are people, they wonder what is a light year, and partly because they've spent so much time, watching Star Wars and sometimes getting the wrong impression. But it's the distance that light travels in 1 year, about 5.9 trillion miles, about 9 trillion kilometers. So light from the sun, 93.5 million miles away, takes 8.3 light minutes to reach us. It travels about 300,000 kilometers per second, or 186,000 miles per second. So Pluto, instead of being 39.47 astronomical, is about AUs away, is about 13 light hours away. The closest star system, turns out, is about 4.3 light years. Now, people said, okay, so these are just different numbers and yardsticks, so big deal. Well, I mean, the Circle K gas station is a mile away. I can say that. I can also say it's 5,280 feet away, which will make people roll their eyes and go, okay, we don't want to spend more time with this guy. But you can see the point, why say 5,280 feet when you just simply need to say 1 mile? Why say 3,669,000,000 miles when you can just say 39.5 astronomical units? That's all this is, just different yardsticks. There's also the parsec, and that's equal to about 3.26 light years away. It's a measure of distance, as we all know, unlike when Han Solo said it can make the Kessel run in less than 12 parsecs. That seemed to imply something besides distance, more like time. So we won't get into that, but that was either an error or a Easter egg for everybody to scratch their heads with. It's derived from parallax second, and it's the distance to a star, which obtends a 1 arc second angle. The closest star then is about 1.3 parsecs away, meaning if the closest star system, Alpha Centauri, is 4.3 light years away, that's equal to about 1.3 parsecs away. A parsec is roughly 19 trillion miles. So, and the observable universe happens to be many, many billions of parsecs wide. Now, this is great. This kind of yardstick is exactly what we need to get out there and measure. So what have we really done with ourselves? Well, I was there watching Apollo 11 that night, I was sitting there in Minneapolis with my dad and my brother, watching it on an old Philco 17-inch black and white TV. And he landed on the moon. Then other men landed later on. And at the end of the day, that's as far as we've gotten, 1.3 light seconds from Earth. Well, I guess that's impressive. But given the size of the universe, this is as far as we've ever gotten. And it all ended back in about 1971 when it was over after the 69 first landing on the moon. If you go to the Voyager mission status, it was launched on September 5th of 77. It's been out there for 45 years. NASA will give you information in various units. It's 14,806,129,627 miles as of 1:30 p.m. yesterday. That puts it at 159, roughly 159.1 astronomical units, or 22 light hours away. Okay, so at 22.1 light hours away. So we send a signal to Voyager, check your cooling. What is the particle density? 22 hours later, it receives it. It does its thing, sends a signal back 22 hours later. So at least 44 hours before we know it, whatever we asked was actually accomplished or not. And it's moving at about 38,000 miles per hour. Now, so this is why it's important to know these, because this is how NASA presents it, and that, by the way, that distance is only 0.003 light years away from us. So, and Voyager is just about the farthest thing we have out there. So while we may have physically traveled 1.3 light seconds, our probe has gone out 22 light hours, and in a universe that's, billions of light years across. So getting beyond our solar system, how do we do that? How do we do that within the solar system and beyond it and so on? So let's get into that right now. So within the solar system, the distance can be measured using lasers or radar. Locally here, for instance, like the moon, the reflected round trip time is measured, and then we can just use, the velocity or the speed of light, which is going to be the case with lasers, times time, divide by 2, because that's the round trip time. So you want to know the distance to it. And it's a relatively simple calculation to do that. There are reflectors on the moon left behind by Apollo astronauts to accurately measure this distance. And they're sitting there. We do it all the time. It's one of the ways we can accurately see that the moon is moving away from us at about roughly 1.5 inches per year. So while we have a full total solar eclipse now, in 70, 100, 200,000 years, it won't be the case. So it is moving away. And that's an easy way to measure how far away something is, even if there's an asteroid coming close to us. But there are other techniques as well. There's also a radar method. We can use that for a few billion kilometers to get out to the planets, and not only figure out how far away Venus or Mars or Saturn is, but also get some structure on the surface features of, say, Venus or Mercury. And so radar can be used for that. A tight, narrow beam is typically employed and also measured by multiple different ways. So we're making sure we're locked onto the right target. We're not getting a radar reflection from something else and not the intended target. But radar provides extremely accurate. We can measure for the signal to get out there and back to us, and we know the speed of light, and therefore get some very accurate information on not only how far away it is, but ultimately how fast it's moving and in what direction it's going, away from us, towards us, or some other angle. And there are a bunch of different technologies out there. We have fixed radio telescopes that can handle the radar part of it. Goldstone has radar telescopes. We have the Deep Space Network monitoring everything out there, including radar measurements. And we also have space-based probes. Unfortunately, as you probably know, Arecibo is no more after being pretty much destroyed by a hurricane. The decision was made to move on and not repair it. So we've lost that one, but there are others out there that we can use. So there's also radio ranging. Round trip signal time is the same kind of methodology. We can send a radio signal to an object. This is really used for probes that can respond to that signal. And this is accurate to tens of billions of kilometers. In other words, getting out to things like Voyager and all that, it's not hard to do. And I believe even Viking back in the day when it landed on Mars could send radio signals and go back and forth and give us distance measurements that way. This method is dependent on signal strength, receiver sensitivity, atmospheric conditions, et cetera, et cetera. And that's why the Deep Space Network for NASA is located in California, Australia, and Spain, so that essentially we have multiple ways of getting a signal out to Voyager or any other probe that we're interested in, and it turns our planet into a little bigger, a larger transmitter than it would be with one single device. Much like, when we talk about the Event Horizon Telescope, which looks at black holes from a planet-sized scope as opposed to a single radio telescope. And it's commonly used for long-range probes like Pioneer and Voyager. So these are great methods, lasers, radio, radar for within the solar system, or just on the boundaries into interstellar space. And they've been working well for us, and they'll continue to be used that way. But for further away distance, there are other methods that are required. So just so you can see here we are down here somewhere close to the sun, and we've got a number of probes out there right now that are making their way in a vast interstellar space. I mean, for Voyager to reach the next star system, Alpha Centauri, if it were to be heading in that direction and the trajectory is right, it will take it at its speed over 70,000 years to get there. Why do I mention that? Because once again, it tells you how far away things really are. So we need a way to measure distances that are way farther than anything we've got right now, anything that we can think of right now. So one method known as a parallax method, I think this is a pretty cool method. It's a form of triangulation. And the reason I think it's really cool is we're already doing it every day, every second. Humans are biologically evolved to use the parallax method. Okay, the way it works is your two eyeballs are roughly about 2.5 inches apart. And if you hold your thumb out there and you kind of squint with one and look with the other, you notice how they flip back and forth. And your brain is then able to look at use that information to determine distance. Now, obviously, there are other factors. I know roughly how big a can of A&W root beer is, and therefore what I should expect. If I see a semi truck, my brain will use that information as well, versus a little smart car, those little things that I feel like you could tip over. But you can tell and you can get an idea for a distance, but that is how we do things. And our mind is able to do that, along with the fact that we're collecting information. As I understand it, if you're blind in one eye, it makes it really hard to drive and judge distances. But how do you apply that to an astronomical distance? You can't use your eyeball. I can't look at a star and go back and forth with my eye and see any sort of a change. That's not going to cut it. Let's face it. our ability to discern two objects that are relatively close together is limited by within a couple of miles, about 3 kilometers. Beyond that, you wouldn't be able to tell if those headlights are 1 or 2 on a car. So, you know, the limit of our eyeballs are just a couple of miles, which isn't going to help with astronomy. So, but yes, there is a way. We can use Earth as eyeballs. Basically, as you might know, we can look at a star of interest in December, and then 6 months later, when we're on the other side of the sun, look at it again. Now that sounds simple, but you've really got to have your instrumentation dialed in and make sure that you're doing this thing correctly and there's no errors involved, and you're looking at how the background stars are affected, and you're able to measure this angle between the two. So we also know that the distance roughly between December and June is 2 astronomical units, about 187 million miles. And then this is how it would look, you know, more visually here as a video. But this is a great way to get out there and figure out how far away a star is. Bottom line is, if you look at it this way, there's the sun, the Earth, and the star of interest, and you end up basically making a right triangle. Now, I'm not going to get into all the math of it all, but I just want to point out how this process works. You have the opposite, adjacent, and hypotenuse of a right triangle. And we know this distance is 1 astronomical unit. And we know this angle because we measured it from the other side here. This is half that total parallax shift angle. So that's good to know. If we know that angle, then we can figure out that distance, that adjacent length from the sun to the stars, and that's good enough. You know, it doesn't have to be from, you know, Stockton, California. Yeah, from the sun to the stars is close enough to be able to say that's how far away it is. Within a, you know, 100,000 miles is great if we can do that. Well, but if you remember from the old high school days, adjacent is equal to opposite over the tangent of that. And for really small angles, which is what this is, these angles are measured in milli-arcseconds, sometimes micro-arcseconds, you know, and so it's extremely small angles. And so you can ignore the tangent of alpha, just call it alpha. And there we go. We can calculate the distance. Distance is equal to 1 divided by that angle in milli-arcseconds. And this method works to about, a lot of people say 500-600 light years, but with advanced instrumentation, we can get it out closer to 1,000 light years, I think, especially with space-based telescopes. By this method, we know that Alpha Centauri is 4.3 light years away. So light will take 4.3 years to get out there. So that's the parallax method, and it's used for a whole bunch of stars, you know, within 1,000 light years, within 700 or 600 light years, there's a boatload of them out there. And if we can determine their exact distance, well, you know, without giving anything away, we can also look at the star, how bright, how colorful, its spectra, all that, and learn a whole bunch of things about it. But all of a sudden, we've got a very precise way to measure. And like I said, it's like a ladder. We've got lasers, we got radar, we got radio, and we have the parallax method. So we work our way. Now we've moved from tens of billions of kilometers to potentially up to 1,000 light years. So that's an amazing way to figure out how far away things are. Again, to get to that distance, you've really got to have pretty advanced instrumentation to do that. Okay. The next rung on the ladder is going to be the brightness method. This is a technique that uses the apparent brightness of a star and compares it to its absolute brightness, okay? So basically, The spectrum of a star is used to measure its temperature, its composition, and ultimately it relates to the luminosity. And the luminosity is what I mean by the absolute brightness. So we can take the spectrum of a star and you can see all the different elements that are, these are the sodium D lines and all that. But we can get a temperature which also allows us to determine not only the elements there, but also, in other words, the composition, but also the temperature. And this is all related in something known as the HR diagram. And I have a different talk where I spend a whole lot of time on this, but this is one of the preeminent, and this is a preeminent diagrams used by astronomers and astrophysicists. I'm sure everyone has heard of this. This is sort of the a high level view of it. We can get really, you know, there's a lot of more information available. But what I'm trying to point out here is that surface temperature will give you, is related to the luminosity. So if the luminosity is 1, which is 1 solar luminosity, our sun, and then we have a surface temperature of about 5,700 Kelvin, which puts us in this range of a kind of a yellow dwarf star, which is where we are. And so by understanding the temperature of a star, by looking at its spectra, we can then relate that mathematically back to its absolute brightness, its luminosity. Now, if you know the apparent brightness and the absolute, meaning its true brightness, as if it were a standard candle that you can be right there, you know its total energy output, then you can easily determine that distance. Okay, and you can, besides looking at the spectrum, remember, you can also look up luminosity from spectra using the parallax method. If I know by the parallax method how far away a star is, then I can use a telescope to look at its color, its spectrum, and I see a star somewhere else that has the same color spectrum, then that kind of tells me it's as bright as this star. This is how far away it is, and how it'll be related. So there's a couple of ways to get to luminosity, the absolute brightness. And once you know that, you can apply that using the inverse square law. What does that mean? It's this equation, the apparent brightness, and if you know the luminosity, you can calculate D, the distance. Okay, this is measured in watts per meter. This is watts. And if you calculate it all out, you can work your way through it. And then the distance is luminosity divided by this times 4 pi. So here's a way to get the distance to the star if I know that. And down here, I purposely made this more grayish, but it works out. And in fact, I like to do what's called dimensional analysis, which is simply make sure all the units come out. Because if the units work, that's half my problem, and I'm better off for it. It saves me a lot back in my school days from throwing up too much before an exam. So we can calculate using the inverse square law. So there's more variables involved here, right? You know, getting that more instruments, and you're collecting brightness and apparent brightness information. So each one of these things as you move up is, I don't want to give the wrong impression, but it's a little less precise than the previous one, you know, because there's a little more, the more variables you have, the more cooks in the kitchen, the more likely it is that things are going to goober up a little bit, or the standard deviation is going to increase. So but it is a very accurate method of determining distance. And without, again, giving things away, I should mention that to the extent possible, astronomers will use multiple ways to get the same information to verify it. This was really true when we looked at gravitational waves, and we use what's called multi-messenger astronomy, multiple different X-ray, gamma ray, gravitational, and optical, all these different telescopes telling you the same thing. Well, here you try to do a similar thing to the extent that you can. And it requires that we have a standard candle, meaning a predictable source. And if we don't have that, it makes it harder, and it's not available for every object out there in space. And it's affected by things like interstellar dust, for example. Fortunately, when we look at things through infrared microwave, we can penetrate a lot of that dust. Anyway, so that's a great way to measure, and it's useful for most of the stars in our galaxy. So instead of 1,000 light years with the parallax, now we're up to 100,000, 120,000 light years of distance that we can go out and measure things fairly confidently. That's a good thing. But let's face it, our galaxy is just one of billions of galaxies. And there's a boatload of space between us and the next galaxy. So we need to keep going. We need to get further out. Next method that I want to talk about. Now mind you, I'm only going to go through about 5. This is the third method. I'm only going to go through about 5. There's probably 10 to 12 commonly used or less commonly used methods, going from the most common. But the Cepheid method is really cool. It gets me excited. It uses, Cepheid stars brighten and dim regularly. I found that to be very interesting. If you look at this, is not just in real time, but this is over days, many days. And sometimes they'll last a month, but they'll brighten and dim, brighten and dim. And that has a powerful outcome. And this dimness and brightening is occurring because of the expansion and contraction of the outer layers of a star and its gravitational pressure and radiation pressure and all of that. So we're not going to get into the life cycle part of it, but that's what they do. Because of this physics that's going on, this thing in its oven, it brightens and dims regularly, and it does so like clockwork. The pulsation period is related to its luminosity. Now, isn't that a hoot? Because think about it. Here's a simple, beautiful, elegant. If I know the period of its pulsation, I can relate that to how bright luminosity, absolute intrinsic brightness. I keep using luminosity, absolute brightness, intrinsic. All are the same. I'm just using them. They mean the same thing, except for apparent, which is how it looks to us from Earth. So it's related. Now there's a long equation. The luminosity, blah, 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 is equal to A log P plus B, where P is the period. A and B are some number constants related to variable stars. Forget about it. Don't worry about it. This is all you got to know. This is what matters. And that's even the simplified equations and all that. So, and that's okay. But, the star goes, brightens, dims, and this is what's going on with it. And I find that to be fascinating. Now I can stare at that all day, but we won't do that. Let's move along. So observing the apparent brightness and period allows us to calculate distance, right? Once again, what am I after? That luminosity, that absolute brightness. If I know the absolute brightness, I also know its apparent brightness. Between the two, we are cooking with gas once again. Apparent brightness is equal to luminosity divided by 4.4 pi d squared. The inverse square law, 1 over r squared, distance squared, just like with any light, right? If you go 1 out, if you go twice as far, it's 1/2, 3 times as far, 1/9, 1/16, and so on, how things work. The universe is elegant. I just love that. So this was a very laborious process. Henrietta Leavitt does not get the credit she deserves. She was one extremely patient, amazing woman, a fantastic scientist. She laboriously went through and did these calculations and found the relationships You know what it's like to have to go through glass plates looking for something that brightens and dims and then disappears and comes back? Amazing, amazing. So that is one way. That's another way. And these standard candles, because they're extremely predictable, they're very precise, therefore they're the standard candle. In fact, if I look at it this way, what it says here is that blah, 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 blah. Where's the important part of it? In the period of a Cepheid's variable star's brightness variation is directly related to its intrinsic luminosity. And because it is directly related and very accurate, it becomes a standard candle. And this method is good to about 10 megaparsecs times 3.26, roughly 33 million light years. Now we're out of our galaxy. Now we're looking at stuff at other galaxies. So the Cepheid method is a great way to measure the distance to other galaxies. And within 33 million light years, there's a bunch of galaxies. Andromeda, M31, is about 2.5 million light years away. And we have found Cepheids there that allow us to accurately determine distance and things like that. So now, as excited as I am about the Cepheid method, oh my gosh, a type 1a supernova, be all the end all. That is one phenomenal way of measuring the distance to a star or a galaxy. Now, these are binary star systems. You have a white dwarf. That's the important. That's why it's a type 1a, not a type 2, not a 1, not a, well, we don't see type 3s, but it is a type 1a, a white dwarf, and another healthy star. Now, as you probably know, a white dwarf is a dead star, period. There's no nuclear furnace going on. It is just a dead star and held up by what's called electron degeneracy, and is taking roughly our sun when it dies, will then eventually, with about 80% of its mass, become the size of Earth and be dead. And that's a white dwarf. So, but a white dwarf next to a companion star has an interesting outcome, which is the white dwarf accretes matter. It grabs the mass, some of the mass from the other star, builds up that mass until it reaches a mass of 1.44 times the mass of our sun, and then blows it all off in a really bright flash. So in other words, it will explode the outer layers away in an incredibly bright flash, and then it will go back down to whatever it is and start accreting mass until it reaches 1.44. Why? Because that's the Chandrasekhar limit, which is a limitation on how much mass a white dwarf can accrete before it blows it off. So that's what's happening there. It explodes within a very specific. In other words, we know that if we see a type 1a supernova, we know that it is of a certain specific luminosity, right? And we know what our sun is, which is 1. Well, we can calculate what a 1.44 mass star will look like, what its total luminosity is, and therefore it's an incredibly great standard candle for us to go out there and measure distances to other galaxies. And we measure the apparent brightness, and of course, you know, it sounds like an old record. We just use the apparent and luminosity and the inverse square law and calculate it. Now, mind you, as I've dug into this stuff, there are other equations involved, a bunch of other calculations, but in a nutshell, this is what it comes down to. If you were to read Forbes magazine article about it, if you read Scientific American or Discover or whatever, this is what it boils down to, without getting into the nitty-gritty of it. But it is an incredibly powerful technique for measuring the distance to another galaxy. But the problem is they're kind of rare, and you got to be looking in the right direction. You're looking here and it's happening over there somewhere, and that can be a bit of a challenge. But it works very well. But instead of getting out a few million or tens of millions of parsecs, you can get out to a few gigaparsecs. Now, let's say a few is between 3 to 5. Let's just say 4 billion light years. Well, 4 billion parsecs times 3 light years, so that's 12 billion light years, and the universe is about 13.8 billion years old. We can get out to 3, 4, 5 gigaparsecs, 6 gigaparsecs. Now we're out to 20 billion light years. So the observable universe, which is expanded way beyond 13.8, we're able to measure things useful, which is fantastic. So I love it. I love it. We're up the ladder. I'm sorry, was that a question for me or something? Okay. I'll go on. What happened to my train of thought? Oh, that's it. So we're working our way up the ladder. And of course, there's more variability here, partly because these are more rare events. So while it's a powerful tool, it's not necessarily easily usable in every case. Next, we can go on up the ladder. And this will be the last one that I'll really focus on before I get into the rest of my talk. But this is the Hubble's law combined with galactic Doppler shift to determine distance. So this is going to be a little bit more explanation required, but bear with me. Let me go through it. Basically, this is Hubble's law. Velocity is equal to Hubble's constant times distance. The value of Hubble's constant is debated. Okay, that's a big deal. You know, you've heard of things like the cosmological catastrophe and all this. There's a lot of discussion. What's going on with Hubble's constant? What is it exactly? Well, the problem is this. Is it 70? Is it 74, 73? Is it 65? Let's see, Hubble Space Telescope had this sort of error bars, Chandra. So we're kind of honing in, you know, it's roughly, I should have drawn a line, but it's around 73 something, but it fluctuates. We don't have a perfect or a great measurement of it. Then there's all this dark energy stuff, which kind of can throw a monkey wrench in the works and eventually change the rate and all that. So if you don't know if you don't know the value of Hubble's constant, and it's not really a constant, well, this could be problematic. But it's a very powerful tool. And, you know, every so often we hear about, okay, here's the latest value. And currently, now don't go looking it up, because I'm sure if we were to look it up, somebody will come back with, it's actually 74.6, or it's 72.2, or it's 73.1. Okay, we're going to stick with 73.4 kilometers per second per megaparsecs. So the universe is expanding, okay, and plus or minus 1.1. So it can be 72.3 to 74.5, somewhere in there. The cosmological Doppler shift helps us prove that the universe is expanding. Edwin Hubble did all of that stuff. Actually, I just gave a talk on that. That was a lot of fun. But it's analogous. Let's talk about Doppler shift for a second. Analogous to a car or a train approaching and moving away, right? You know, come on. When I was a kid, we used to stick a penny on the train track and see if it would flatten it. And then we'd hear it and go, eew, like that. As the waves are coming at you, it's being compressed and it sounds higher pitch. The sound waves, as it goes away, it expands and sounds lower pitch. Same thing happens with electromagnetic radiation. Same thing happens with light. So blue shifted objects, stars, galaxies, etc., that are approaching us, they're shifted towards the blue region. Red shifted, they're receding away from us. And spoiler alert, the universe is expanding everything ultimately is red shifting. Sure, on a local level, something like Andromeda is coming to bang into us, so it's approaching us, but at the larger scale structure of the universe, it's all expanding. So red shift, blue shift. Huh. Just thought of that Korean show, Red Light, Blue Light. I wonder. Anyways, green light. I don't know. Forget it. I never watched it besides one episode. Let's see. I don't think I was the target audience for it. The extent of spectral shift allows us to calculate basically the relative velocity. So here's what's going on. You have the normal spectrum right here, and then you have, are you guys able to see my cursor move? I always wondered about that. Oh, good, because I hate to be pointing stuff and nobody sees it. And then when it's moving away, it's shifted towards the red. These lines are shifted. The degree of shift represents the amount of recession velocity. So anyways, by determining the recession velocity, we can then determine the distance using Hubble's law. So let's talk about that. So that value Z, which is the sort of the recession, the Doppler shift value, is going to be the observed minus the rest, which is what we saw. One is the normal, unchanged, the actual, and the other one is what's observed. And then we can do a calculation, and V is equal to C times Z, which is the speed of light times this Doppler shift. And you can go back to your equation here and calculate this. And if you know what C is, if we know what Z is, boom, you've got your answer. I'll actually have an example I'll show you, but it's used to measure the distance out to many, many billions, actually to the ends of the universe, just about. And it's a little more fragile because it has a problem. And that problem is that we don't know exactly what Hubble's constant is. It fluctuates. Therefore, our answer can change a little bit. And so, but you know what? If you're going to talk about something that's, 40 billion light years away, plus or minus 4 billion light years, isn't going to affect the price of anything locally. Okay. But it gives us an approximate relative understanding of what's going on. So that's essentially the galactic method. So if we observe a galaxy with a redshift, Z is equal to 0.05, well, we can use this relationship, observe minus rest. So we know Z is 0.05 and Z is equal to VC. V is equal to, just rearrange this equation, CZ, where C is the speed of light. So then we do this 0.05 times the speed of light, which is 15,000 kilometers per second. Now we can use Hubble's law, where D is gonna, you just rearrange this equation, is V over Hubble's law, Hubble's constant. And now you've got what you need, 15,000 divided by 70. Everybody's in the same units, kilometers, and you end up with 204.5 megaparsecs, or whatever that object is. It's receding away from us, but it's about 667 million light years away. So that's sort of the easy version. There is a heck of a lot more involved in the overall calculations, but you have to take a lot of factors into account. Don't forget, we're moving, the Earth is moving, the sun is moving, the galaxy is rotating. So how do you figure all that? You got to take a bunch of different things into account. But at a very high level, this is how this works. Now, I mentioned, gosh, what if Hubble's constant wasn't 73.3? What if it's 76.9? Well, this 667 becomes 636. What if it's 68.5? It becomes 740. You get the joke. It's a little bit dicey. I wouldn't exactly rely on it. But, well, I won't say it's rocket science, but it's good enough for government work. And I know I spent about 5 years in a government lab, so it'll work. So we've talked about the various, the key methods that I wanted to go over, and I know we're going to be coming up on time not too long, but I want to make sure that I had a chance to go over those. But remember, again, in some ways that the universe is unimaginably large, right? Astronomers, they're smart guys. They're not just smart, but gosh, they're like a bunch of George Lucases and Steven Spielbergs, if you ask me, of science. So distant measurement tools are built on the results of other tools. It's a ladder. And therefore, now do I think tomorrow something's going to happen and everything's going to get shifted and all of a sudden we're going to have to rewrite all of our distances? No. But do I see tweaking and other things happen that could affect numbers by 0.5%, 1/4%, 1% maybe? That's possible. But we're already in the ballpark, more than in the ballpark. It's a continuous improvement process. All right. So radar within the solar system, parallax nearby, brightness methods all throughout the galaxy, Cepheid's other galaxies, type 1a, even further galaxies, 1 billion light years, and even further, more than 1 billion, several billion. And even further, we have Hubble's law and Doppler, cosmological Doppler shift occurring. So there's a whole bunch of these methods and several others. There's these methods that we can then use to help us or take it to their edge, where maybe the edge of this allows us to go into this and feel good about the results we get here. And the edge of this allows us to feel good about the results here. So we build upon each other and it all ties together, but it's not a house of cards. Okay. There's a lot of logic, a lot of mathematics and other things that has gone into this. There are other methods. I'm just going to mention them real quick. We're not going to go into it. Cosmological background radiation. We can study the CMBR and look at micro fluctuations in temperature. And there's a way that relates it all back to a standard ruler that astronomers can use to measure throughout the entire universe distances. Gravitational lensing. Okay, analysis of light from which distorted light from gravitational fields of massive objects like very distant galaxies and things allows us to measure distances. I have not studied that method myself. It just sounds like it's going to be way wacky out there, but I can't wait. There's the baryon acoustic oscillations, which basically is a fancy way, unless I've got it wrong, is about how matter is the density of matter and at the large scale, and they can use that to measure distances. As you well know, I'm assuming this means like baryonic matter, which is normal matter, versus dark matter and dark energy and all that other good stuff. But these are 3 other methods. There's probably another 3 or 4, which we're not going to get into, but there are more methods, and I just wanted you to know. So we've talked about locally within the solar system, lasers, radar, radio. We've talked about parallax. We've talked about brightness method, talked about Cepheid, type 1a, and Hubble's methods. So those are what I wanted to cover, but what I want to do is finish off by going through really a real quick survey of what is our place in the universe, in this vast, large. So we know all these distances. What does it mean? Well, the Milky Way is 13.8 billion years old. Got its name from Romans and Greeks. And spiral galaxy, a barred spiral galaxy with over 200 billion stars. It varies depending on what book you read. And by the way, I've had people tell me, oh my gosh, how did you get a picture of our galaxy? That is not a picture of our galaxy. Everybody knows that. I know you all know that. We can't see our galaxy. We look at it from the inside. This is the first photo I ever took of the Milky Way, so I have to show it whenever I can. Okay. I just got to. I'm really proud of my photo. So our galaxy is about 587 quadrillion miles, let's just say 100,000 light years across. Okay. We're located halfway on the Orion Spur, and basically we're in the backwaters of the galaxy. And we have a supermassive black hole, Sagittarius A star, with about 4 million solar masses, and everything is in motion. That's why it's so tough to be able to determine where things are exactly. Earth is rotating, we're going around the sun is orbiting around the galaxy is rotating, and everything in the universe is expanding. All kinds of things are happening. The guy who created this is really amazing. I ended up writing him, and he said, feel free to use everything that I've produced. I always make sure he gets credit, James O'Donnell. Anyways, for centuries, here's the update that I want to give you. For centuries, astronomers studied the Milky Way, and basically we thought we had a good understanding of its structure. Well, an accurate structure is hard because we can't see our galaxy from the outside. We only look at it from one corner on the edge of the galaxy somewhere. So, we can't see it. So it's pretty much, we're pretty sure it's a barred, not as in the barb, don't confuse barred with barbs. I mean barred galaxy, spiral galaxy. And, but it turns out recent studies show that it may be a little bit different. In China and Australia, they did some work on Cepheid stars. They looked at 1,300 of these Cepheid stars throughout our galaxy and determined that, it doesn't look like we're kind of that flat disk we think we are, okay? And as it turns out, the Milky Way is not flat, but it appears to be warped and slightly twisted. Probably looks more like this from the outside. And now, that's okay. There's a lot of galaxies out there that are like that, so we're not the only one. So that's the good news. Or is it, who cares if it's good news or bad news? It's the way it is. So it becomes progressively twisted on its outer edges. We don't know exactly why, but we think there's forces from globular clusters, dwarf galaxies, and all that are affecting us. The rotational rates and things like that have led to it. But there are many other. This is ESO. This is the galaxy labeled ESO 510-G13, which is also a warped spiral galaxy. Turns out the universe is filled with all kinds of galaxies, right? You've got elliptical, spirals, irregulars, and then they have their own subheadings. And my favorite is the Sombrero galaxy. I just love that galaxy anyways. But in our galactic neighborhood, we're part of a local group. The Milky Way is part of this local group of galaxies in the Virgo cluster. And this is part of the Virgo supercluster, and which is also one of many structures in a 93.5 billion light year across observable universe. So it's a pretty massive universe. It's 93.5 billion, as you well know, because of the expansion rates of the universe. But that's where we are. We're part of a big observable universe, and it's 13.8 billion years old. I've already addressed it, but the reason people ask is, well, why can't we just say it's 27.4 billion light years across, 13.8 in that, and 13.8 in that direction? Well, because space is expanding initially due to inflation, and then later on and now, and for the foreseeable future, effects of dark energy. So it's continued to expand and continues to expand. So as a result, it's about 93 billion light years across. Okay, so I was trying to finish things up in about 45 to 50 minutes, which is about the case. I do want to point out that this is also one of those amazing photos which everyone in the world should have seen. And that's Earth located out there, Earth seen from out there, taken in 1990 by Voyager at about 39.8 AUs away, so 3.7 billion miles away. And as Carl Sagan said, look again at that dot. That's here, that's home, that's us, that's everything. Everything in the past, present, and future for us. So that's our place in the universe. And that's our family photo. All right. Well, I think that pretty much concludes, and hopefully you were able to follow along. And if you have any questions, I'm more than happy to address them. I should point out that these doggies were very good, especially the two on top, watching me do this presentation and practice it. They liked it, or maybe it was the treats in my pocket. But Tristan and Rhonda up there on top, and then there's Louis the Chewbacca. Anyways, many thanks, and I really appreciate it. I'm a big fan of the Far Side.
Excellent.
stop
Thank you,
sharing.
Awanish. Just give Awanish a hand. Thank you.
Hopefully that wasn't beneath you guys too much in any way. And
Pardon me?
when there's any questions, now mind you, I will do my best to address them. It's easy to stump the chump. So I'm letting you know that ahead of time. That being said, Tim may not care about this, but you can reach out to me in email if you have any additional questions. And Tim, I don't know if anyone's ever does this, but I'm also more than happy to PDF my slides and give it to you to distribute if anyone's interested.
Well, that's very generous. In fact, I was going to comment that slideshow that you have, that presentation is chock full of wonderful illustrations, formulas. I thought that was fantastic. So yes, we'd love to have that. In fact, Eric's has been recording this. So it'll be on our YouTube channel for replays if anybody wants to see it again or to get more details.
Great.
So yeah, let's have any questions from here in the room. Come on up to the microphone. If you're on Zoom and you have a question, just look for an open spot and jump right in. So anybody have questions? Well, I'll start off then. Awanish, I do have a question. You mentioned astronomers measuring the parallax angle. Can you talk to us a little bit about what kind of instrumentation there might be on a telescope, or can an amateur measure that parallax angle?
No, an amateur can't. You can actually go out there and measure things like, for example, if you want to measure the moon, you can do that. You can do it from here, and then you can go, I don't know, a few hundred miles away and measure it again, or have someone measure that angle at the same time as you're doing it and then get that information. But if you're talking about trying to measure another star, you can't. You may be able to do that with some of the inner planets, and otherwise it's going to be very difficult. And you're going to need some more advanced instrumentation. I don't know the exact name of the type of the instrumentation, but when I check this out, what I also tend to do is when I give you these slides back, I will have a summary of any of the Q&A I get with answers on them. So I'm more than happy to look it up exactly what we can do by ourselves as amateurs and what does a professional do.
Very good. Thank you.
No, I have a question. Can you hear me?
Yes, absolutely.
Going back to radar, I've always wondered about this. Since radar reflects off of metallic surfaces, is there just enough surface metals in most objects to use radar?
Yeah, but it doesn't have to be just metallic surfaces. I think depending on the density and the type of frequency being used, it's like they use ground penetrating radar as well on Earth and things like that. So no, we don't use it on gases and things like that, but you're using it on rocky planets, which does have metal in there. I think so yes, but the hardest part of it is making sure that you're getting Mars and not Phobos. You're getting the asteroid you want, not the one a little bit further away. And that's going to be the trick, using a very tight beam radar that has minimal amount of spread occurring. And therefore it's limited in how far it can go. Same thing with laser light.
All right, well, thank you.
Any other questions? Well, I hope you guys enjoyed it at least. So
Yes, any other questions in the room here or on Zoom?
my mic doesn't seem to want to work, but my question is twofold. How long do scientists estimate it would take Voyager to reach the light year measurement, second generation? Okay, second question. How long will it take Voyager to reach a light year? Well, if they're saying it's 70,000 years to get to 4, so it's going to take, and it's gone about 0.002 or whatever. So let's just say it's going to take about 17,500 years, roughly, to get to 1 light year out. Based on the way things are, the way it's moving, there's no reason to think it's going to slow down, because it's just coasting now, unless it encounters something. Second question, with blue shifting bodies such as M31, how are bodies measured from light years to light minutes? How are bodies measured? I'm not sure if I follow that, but I'm assuming what that means is, if you look at how far an object away it is away, if it turns out to be in the order of, billions of miles, or even 1 trillion miles, let's just say, you can convert those, whether it's a light minute or a light year or number of light seconds. I mean, it doesn't matter. If you know what a light year is, that's going to be so many light minutes. If it's 1.3 light seconds away, that's like the moon. Well, that's equivalent to so many light minutes, so many light hours. I may not have gotten that question understood well, but those are just 2 different factors of how light distance is measured.
Go ahead.
Any other questions?
Yeah, I do have a question. Between Cepheid variables and the type 1A supernova, I have heard that galaxies tend to have enough planetary nebulas in it that they can find a peak brightness of planetary nebulas and use that as a distance measurement to other galaxies. Have you heard of that?
Yes, I have. In fact, I didn't list it, but there is some paperwork. I tend to, before I talk, I keep a lot of paperwork around me, somehow thinking I'll read them when I need to, but I don't know where it's what. Yes, I have. And that's another method which I'll include in my lecture notes when I send it out. I have heard of it. I'm not familiar with the methodology, but yes.
Great question. Okay, if there's any other questions for Awanish, well, thank you again, and I appreciate you very much.
Thank you so much for your time. I will head on out from here. You guys have a great evening. Stay dry. Bye.
Thank you so much. Okay, Eric, you'll shift over to Jeff's presentation, and we'll give Jeff the floor now.
Can I go towards the screen rather than?
You can, yeah, that microphone up there will turn it on. Hold it, or you can.
Thank you. Hi, guys.
Just a second.
Eric says, give him a second, so we'll have to wait.
Your presentation is important to us.
Yeah, from our vantage point, it looks like Jeff has white hair and is wearing glasses now with a white turtleneck. Yeah, that's you, Dennis.
Yeah, that's Jeff on the left.
Yeah, I'd like to congratulate you for staying awake. You usually sit back and yawn through stuff.
I
Okay,
had,
are we ready?
I had a meal and then I was doing some, web searching on that radar question.
Are you ready yet? Okay, I've been given the go ahead. So this first slide is Tim's idea. First of all, the Messiers are named after Charles Messier, who was a comet hunter. And he would stumble across something and go, hey, all right, I found a comet. And then it wouldn't move. And we realized, oh, that's something in the sky. So we had to start cataloging the non-moving fuzzies in the sky so that he wouldn't accidentally declare that he discovered a comet and it wasn't true. So the picture on the far, I guess that would be our left there, is Charles Messier. He didn't finish the list. A gentleman by the name of Machine finished the list. And he's also the guy who measured the French coast from the North Shore to the South Shore to determine the distance from the pole to the equator. And dividing by 10 million gives us the meter. So Charles Messier and Messiaen were the two guys who came up with the 109 objects on the Messier list. I know there's 110, but M102 is either a repeat or a mistake. So there's really 109. The gentleman in the middle is a good friend of ours. He passed away from COVID last year. He is Don McColtz, who discovered many comets, just like Charles Messier. And he's also famous for having done about 5 trillion Messier marathons. And he even wrote a book on it. And he's a great observer. He spends thousands of hours looking for comets, and he'll get one about every 1,700 hours of observing. The guy on the right is the absolutely most handsome human being ever born in this world. Yeah, yeah. It's looking at me through the eyepiece. That's me. Okay, I don't know why this picture's up here. Anyway, I've done a few Messier marathons. I guess that's why he's got this up here. I haven't done one in a few years. So this one coming up this month will be my first one in I don't know how long. I've done maybe 12 or 15. I really don't know. I have never done all 109 in one night. I never get M30 ever in a Messier marathon. It rises in the dawn in the southeast, and I fail on it every year. And that's okay. I can admit failure. Okay, so I'm glad my pictures with those other two. Those other two are awesome. I have discovered a grand total of 0 comets, by the way. I've discovered 2, but unfortunately they were already discovered, darn it. Okay, next slide. Yeah, true. Next slide there, Eric. Okay, so there we go. This is why you can have a Messier marathon. This is a map of the whole sky. And I've done a little drawing on it. I've also cut it and moved it and situated it so you can see why a Messier marathon can happen. All the red circles groups where Messier objects are, and you notice that in the big blue circle, there are no Messier objects. And so if we can get the sun in the middle of that thing, then we can see them all in dark skies. So if you look at the yellow stripe is where the sun is during a Messier marathon. It's on our right side around March 15th, and it's on the left side around April 5th. And right in the middle of that yellow strip is March 20th. It's the best day to do Messier marathon. To the right, then that it makes it more difficult to see the objects to it as they're rising in near daylight. And if you get too far to the left, the April 5th one, then the guys there in Cetus, they start to set too soon and we miss those. So since we are doing a March 18th Messier marathon, then our sun is going to be on the right side of that strip. And you'll see, I guess it's ridiculous for me to try to point to this. Can you point with an arrow there? Okay, well, Okay, don't worry about it. I'll just say, if you look at the Pisces Austrinus there, right above it in Capricorn is M30. Notice it's right on the edge of that blue circle. Well, that means come 5:30 in the morning, when it rises, we want to get that 109th. What? Okay. Okay. When we get to that 109th Messier, it's pretty much daylight. And so that's gonna be tough. So, if you look at the green lines, the one that goes from bottom left to upper right is the horizon at sunset. And the one goes from the bottom right to the top left is the horizon at sunrise. And so you'll see that you can see the stuff to the left of that lower left to upper right line in the evening, and then everything else all night long. And then the stuff to the right of the lower right upper left line pre-dawn. And in the top, you'll see that in Cassiopeia, Cepheus, and Andromeda, we can see those guys in the evening. So you get two opportunities at those guys in the top V. So we're going to have the Messier Marathon on March 18th. That's the date of the high altitude star party, but we're going to pull this off at the Highway 4 site. And Tim has asked me to take Chester, my 24-inch scope, and do a blow by blow, object by object whack on this thing and just see how many we can all get. So everybody's invited to come along and play. And I do have a method to getting them. A lot of people think you just keep going to the left all night long, but it's more than that. You have to kind of bounce around a bit. So anyway, if anybody wants to play Messier Marathon, you don't have to stay out all night. We don't have to do them all, but we'll keep plugging away until nobody's left to play. So if you can go to the next slide, Eric. The way I do it is I do it in about 15 groups. And the first group is
Yeah, you start right at sundown.
I start before, well, yeah, I start right after sundown. And okay, there we go. The first thing to get is M45, because you don't need a telescope and you don't have to wait till it's dark. So before it's dark, yes, the sun is down because no Messiers can be seen when the sun's up. But once the sun's down, the first thing you can nail is M45. It's a naked eye. You don't have to see them with a telescope. And Kerchak, you got it. Then my group 2 is 74 and 77, which are going to be, because they're getting low, it's getting dark, and they're not the easiest to Messiers in the list. And after that, group 3 is M33 and 32 and 31, and group 4 is M76 and 52 and 103. And so that groups 1, 2, 3, 4 probably could be done in 10 minutes if you get the game on, and a little longer if you don't. Okay, next slide. So group 5 is your Orion, Canis Major, Monoceros, and Puppis group. And, you know, the trick is to think ahead, know where they're at, know where to point your scope, get it and move on. You don't want to look at the Orion Nebula for 20 minutes. You want to say, there, I got it, and move on. Okay, next group. So this group here is the Auriga group. Next group. And here's your Cancer group. 2 objects. Bing, move on. And next one. Okay, so the Big Dipper's got a bunch of stuff. I circled a couple in green because they are actually in another group. But if you want to get them now, you can get them now, and then you don't have to worry about them later. Big Dipper will be a little bit upside down, but you know, that's okay. M40 stinks. It's a double star. It is actually kind of difficult. Nobody knows why it's a Messier. Okay, next slide. Okay, Leo has 5. It's basically M65 and M66 are a one-shot deal. 2-for-1 specials are great. Click. Okay, next group. Okay, so this is the first unfun group. If you look at group 10, they are the Marsharian's chain in Virgo. And I don't know, there's like 10 or 11, maybe 12 galaxies there. And there are no stars to star hop with. So you basically find the first one, then you galaxy hop from one to the other. So that's your first challenge for the night. And the other ones there in group 11, they're just kind of on the same chart. So I had them on there, but that group 10, that can be the less fun of all the groups. Okay, next slide. So right about now, you've cleaned the sky off and you have to wait a while for the sky to rotate. So this is where I either take my nap or I start whacking Herschel objects, because sometimes it's fun. One of the things I've done before is Herschel Messier marathon, where you get 100 and something Messiers, and you try to get 100 or more Herschels and try to pull off a 200 object night. So that 3-hour period of time that you're waiting for the sky to rotate, it's a good opportunity to do that if you're crazy enough and stupid enough to do that. Okay, so this group here is also a difficult group, not because any of them are hard, but because it's spread over a large piece of sky. And so I put them in one group just because they kind of belong. Okay, next one. Okay, then you get over to the globular cluster game in Ophiuchus and Libra and Scorpius. Okay, next one. At which time you do the Sagittarius game, Sagittarius and Scutum and part of Ophiuchus. So those are all really good objects, but when you start getting up to the open clusters up there on the top end there, sometimes they just kind of start running into a challenge. And by this time of night, you're kind of tired. So, you know, that's how it is. M75 is way over there on the bottom left, but I don't have it in this group because it's just an inconvenient thing to scoot all the way over and get that and then come all the way back. Okay, next group. And this is the last group. So if you, second to last group, sorry. If you look at this one, you got M75 this time and M15 and M2, and they're not the brightest objects out there. So, you know, they're a little rough. And then the next group is our last group. And you get click 72 and 73 up there. But then the problem is M30. And what you can't see here is that the horizon is right at the bottom of the M30 and it's already daylight. And you can either lie and say you got it or you can live without it, but that is going to be the problem object. So anyway, you know, nobody wants to scare anybody away from doing the Messier Marathon, but it's a lot of fun to give it a try and, you know, stick it out as long as you can. If a person wants an Astronomical League certificate, you have to find them all yourself. But if you come out on the 18th and we find them and you click them off, our club will get you a Messier certificate if you get all the Messiers, whether you found them or not. And so we're still going to try to make this fun and get them all. Tim, was there anything else you wanted added on to that? All right, thank you.
Great, thank you, Jeff. By show of hands, anybody interested in coming out for some or all of the March 18th Messier Marathon? Can you switch it to the, here, can I see the Zoom people or? I was curious if anybody on Zoom is thinking about coming out for some of the marathons. Laura, excellent. Yeah, and remember that if somebody else doesn't come out, that we can lie about the whole thing. Yeah. Yeah. Okay, just a few announcements here. You can see on the left our upcoming SAA meetings and star parties for March. Tomorrow, Jeff, Saturday, you've got an amateur telescope makers.
Yep, 10 o'clock to 2 p.m. 10 a.m. to 2 p.m. My stop in Electric.
Excellent. For that. The 18th, like we talked about, the Messier Marathon, new moon on the 20th. And then going into April, you can see all the upcoming dates. Eric does an excellent job of keeping our website calendar up to date. So go there if you don't catch all these dates. What's not on that calendar though is on the right-hand side is Doug's public outreach events.
You're not done. The Stockton Astronomical is public outreach.
I stand corrected. They're not Doug's events, but it's Doug's responsibility to find volunteers for these events. Okay. And so that's why we show them and advertise them here in the newsletter. So, and that's the sign up sheet that we passed around. So there's several coming up still in March and many in April. Some of them are back-to-back days, Friday, Saturday. We're at Delta College, or then the STEM event on Saturday during the day, and then March 25th, astronomy in the park at night. So looking forward to everyone coming out for those.
Can I say something?
Hey, Bill,
about
go
that?
ahead. Yeah.
We were going to try that with the STEM Expo that was here a couple of weeks ago. And I think the people that attended the STEM Expo here were kind of glad that it was raining cats and dogs, because we wouldn't have to go out to the park that night and do a tour. And so whoever can volunteer for one or the other, please do. And it is hard on the back and the legs and everything else.
Yeah. We need more volunteers.
On those 2 days.
On the Saturdays, on March 25th and on April, the April 22nd, 23rd.
Yeah.
So, people who help out during the day.
Jeff, you had a comment?
Yeah, I know that the Messier Marathon is Highway 4 on March 18th, but technically our Highway 4 start party is and the Highway 2 start party is March 18th. We're going to do a marathon on the 18th, Highway 4. So I want to say that the 11th is still a Highway 4 start party.
Okay, I didn't get it on the slide here that way.
I just want to make sure the 11th and 18th will be a Highway 4.
Okay. Add to this list on the left side, March 11th for Highway 4. Also kind of a warm up to the Messier Marathon on the 18th. So, okay. One thing I did want to point out is April 29th. Put that on your calendars, everyone. Let's all get together out at Oak Grove Park for Astronomy Day, the SAS potluck. We'll have a good time at those. And then that evening is Astronomy in the Park. And we'll make sure all this gets in the newsletter as well. Again, contact Doug or anybody, any of the board members, just reach out if you're available to, as a volunteer, to come out, with or without your scope to these public outreach events. We've got loaner scopes, we've got club scopes. We can use folks that are not working as telescope at the time. So please come out. You'll have fun and you'll get a lot of reward out of it. Okay, kind of as we wrap up here, I did want to say again, thank you to our speaker. I think he's left now. Thank you, Christy, for the refreshments this evening, and to Doug and Mike for the coffee. And then did everybody see the sign-up sheets or get a chance to look at them? Okay. I'm thinking that about wraps it up. Is there any other business? Comments? Criticisms? We don't have time for them. So with that, I'll declare the meeting adjourned, and thank you all for coming this evening.
Thank you. Good meeting.
Oh, I've got the gavel.